Hello world, this is Craig. My next video I'm going to do is going to be decoding the addresses on some of the MIL/MOD memory boards. And in looking at that, I got to thinking, well, maybe I want to talk about the exclusive OR first and how it's quite an amazing little gate. It requires a higher level of thinking. We can look at a schematic, and even my addled brain can look at a schematic and look at something like the sync signal that's coming out here and say, okay, well, that's double inverted, so it comes out and it comes down and it's inverted again. So now we have the inverted of the sync signal that is ANDed with the phi 2 of the clock. So if phi 2 of the clock is high and the sync signal is low, then this output is high and that comes over, that goes into this AND gate. And so you can work your way through a schematic fairly easily just thinking about the basic of the logic gates, the ANDs, the ORs, the inverts, and their complements. But when it comes to the exclusive OR, you need to think a little bit differently. The exclusive OR is operating at a higher level. So let's talk about what the exclusive OR is doing. Here's our exclusive OR. This is the symbol for it. Okay, and we have A and B, truth table, A, B, 00011011, and then the output. It acts a lot like a regular OR gate. If 0, 0 are the inputs, the output is 0. If either of these are 1, the output is 1. But the difference is this is an exclusive OR, and by exclusive, we mean mutually exclusive, so that if both are 1, it's mutually exclusive, it has to be equal to 0 again. And this is what makes the exclusive OR different than a regular OR gate. If you think about the truth table when you're trying to work through a schematic, it's really tough to take this into account all the time and think, oh, well, if that's a 1, 1, now this is going to act differently. So with the exclusive OR, it helps to think more about the function, what the intent of the designer was, rather than the actual truth table. So that's why I say the exclusive OR is really the Rorschach's test of the logical person, or of the logic designer. If you ask one logic designer what they see, they'll say, well, obviously that's a half adder. And you ask them to explain. Okay, well, here's my half adder. If I have A and B and I bring them into my half adder, and this comes out, and let's say I add another gate to this, an AND gate, and I look at this. Now let's see what we've got. This is my truth table. Here's A and B, 00011011. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1. 1 plus 1 is equal to 0 with a carry of 1. So obviously this is my sum and this is my carry. So it's a half adder. And if you want to, you can expand this out as many times as you want and get a full adder for as many bits as you want. And basically, the exclusive OR works very well as a half adder. This sum is equal to A plus B, and if it rolls over, there's a carry bit that you can get with just an AND gate. Okay, well, I can accept that answer. You ask the next person, what do they see? They say, well, obviously, this is a parity generator. Okay, let's look at that. Explain that. Well, here is our parity generator. We've got 2 bits, A and B. They're going to come in, and we want to know, they're going to come in, and we want the output of this, like we're going to send it serially or something, we want the output of this to always have even parity. Well, let's look at what we get. If A and B are 00011011, this is our even parity, and then here is B and A. So A and B and our even parity, 0, 0, the even parity needs to be 0 so that we have even parity. If A and B are 0 and 1, the even parity has to equal 1 so that we have even parity. If A and B are 1, 0, the parity bit has to equal 1 to keep our parity even. But if A and B are both 1, then our parity bit has to be 0 to keep the parity even. So obviously, this is an even parity generator. And we can extend that for as many bits as we want, and we can also use that to create a parity checker on the other end. Okay, I'll buy that too. It's not used very commonly for that, but I'll buy that. Next person, what do you see? Well, obviously, it's a programmable inverter. Let's explain. Here's our programmable inverter. It comes in, we have A, and then we have our programming bit, which for right now, let's just say we're going to connect that to a switch, and that switch is either normal or it's invert. Okay, and let's look at the output. Well, here is our switch. This is our invert switch, and this is A, 0, 0, 0, 1, 1, 0, 1, 1. So if our invert switch is off, then the output is simply A. We put a 0 in, we get a 0 out, 1 in, we get a 1 out. But if we flip our invert switch on, now the output is equal to the inverse of A. So obviously, this is a programmable inverter. We have a bit here that we can program and either invert the signal or not invert the signal. Same test on the next person. They say it's an equality generator. Well, let's look at that. We have A and B. They come into our equality generator. And we have our truth table. Here's A, B, 0, 0, 0, 1, 1, 0, 1, 1. Well, if A and B are the same, this outputs a 0. But if A and B are different, this outputs a 1. So if I just put an inverter on this, this obviously gives me A equals B. So here, if I invert that, I'll get a 1, 0, 0, 1. And so this means that A equals B. A is not equal to B. A is not equal to B. Or A equals B. So generally, those are the 4 ways that we will see an exclusive OR in a circuit. If we look at all of the schematics for the Mod 8 system, the only place the exclusive ORs show up is for the programmer, and they use it as the programmable inverter to complement the address right before they program it to the EEPROM. So I would say that generally, the exclusive OR is most commonly used as either the programmable inverter or as the equality tester. Much, much less frequently is it used as a parity generator or as the adder, simply because there's better ways of doing, if you need more than 1 bit of either of those, there's chips that do parity generation and adding. So the upshot is that when I look at a circuit and I see an exclusive OR, I stop thinking about the truth table for an exclusive OR, and I first try to identify what the designer's intent of that, and it just makes reading the schematic a lot easier. Then, of course, there's the people that you show this to them and they say, well, that's a goose flying with his legs out. Or it's a really squinty-eyed laughing clown with his tongue sticking out. All right, well, let me know what you see in the comments below. And thanks for watching. The next video, I'll be doing the memory address decoding for some of the MIL-MOD memory boards. All right, thanks for watching. Bye-bye.